Okay guys, we're going to start working on AC, start some videos that will be covering that, and as far as those that's following on the other videos series, both the TV circuits, there will be more videos coming on that, and the RCA radio, there will be more coming on it, in the next few days, so don't worry about those. But I've had some requests about AC circuits and questions about AC and everything dealing with AC, so we're going to do a series on AC. It's going to be somewhat lengthy. I'm not sure how many videos, but we will get through it. Today we're going to do some basic information, some math and stuff. Unfortunately, for those who do not like math, AC, we absolutely got to deal with some math. There'll be some trig and stuff in there. So anyway, first thing I wanted to show you, and what we're going to talk about today and stuff, we're going to talk about AC itself a little bit, and on the next video we'll probably go into it even more, because I doubt I'll have enough time to do all of it, talking about an AC signal, or AC. Basic a sinus audio signal, kind of like what you see on the screen here. Let's see if I can zoom in to that. Now, if I take a voltage measurement of this, what I've got is I've got a cord plugged into an outlet on my variac, and I got it set to a certain voltage. And on the probe, I've got it. It's a times 10 probe, and which basically means that when it's set on times 10, whatever this is set at, we multiply by 10. So the vertical is set at 5 volts, which is max per division. Well, with the times 10 probe, then that is actually the same thing as now it's 50 volts per division. And the AC signal centered here is each division is 50 volts, so we got 1, 2, 3, and some change. Works out approximately around about 170 volts, 169.8, somewhere in there, but about 170, just to round numbers off, one peak. Okay, peak to peak would be about 340 volts. Now, I also have a digital voltmeter tied into that, and we're dropping just a little bit. We'll raise it just a hair. It's a nice thing about variac, we can adjust it. So approximately 170 volts peak there. Let's look at and see what we're getting on the voltmeter. And oh wow, it says 120. Well, is that wrong, or is that wrong? Maybe I need to do some adjustments. You know, maybe they're both wrong or something. Maybe they're out of line or need to be fine-tuned. So I've got my fine-tuner here. Of course, my daddy always taught me, if all else fails, just give him a bigger hammer. So I could get the bigger hammer out. And sorry, I bumped you. A little bigger hammer. Think that'll work? We can fine-tune that. Well, before we do any fine-tuning, let me point out something. Scope measures the actual, it measures the actual waveform of the AC signal. So it's measuring peak to peak, what is known as peak to peak voltage. So one peak at approximately 170 volts, whereas the digital meter is actually measuring what is known as RMS, or effective voltage, which works out to be 120 volts. This is your AC line voltage that comes in your house. So if you got approximately 120 volts coming to your house, the peak to peak voltage, one peak will be 170 volts. So what is RMS? Well, we're going to show you and show you the definition of it and work that out. And so we'll get to that. Just give me a second and I'll clean this mess up, and so we can work on that. Be back in a second. Alright guys, now this is the definition for RMS. RMS voltage, it's an integral equation. It's what this little stylized S is integration calculus. It's 1 over t. T is period or time, period of the wave, the amount of time it takes for one complete cycle. So anyway, 1 over t, the whole thing is underneath the square root, so it's 1 over t times the integral, which is known as a definite integral because it actually has this on here. These are the limits. So it's as it goes from 0 to t times of v squared p. P is peak. V is the voltage peak. This is just one peak of the voltage. So in other words, just like we was figuring on there, you've got a sine wave. We're just interested in this. That's what that VP is. It's just this one of these peaks right here. That's all we're curious about. So V squared P times sine squared of 2 pi ft. T again's period or time, F is frequency, 2 pi is just a constant that deals with the sinusoidal wave. We use it. dt, standard for integration. So that's RMS. So does that mean that every time you got a little sine wave there, it's showing up and on your scope, or you see or you know that it's a sine wave, you know what the peak voltage is? If you know the peak and peak voltage, you just take 1/2 of that and get your peak voltage. That you're going to have to plug it into this and work this problem out and stuff? Well, not entirely, and I'll show you why. We are going to solve this problem. Now I'm not going to keep, there's a few things I'm going to do here that just to save some time and everything. For one thing, this little mess here, we're going to call U just for right now. The only reason I'm going to do that, it will always be the 2 pi ft, but I don't want to have to just keep writing out 2 pi ft. I've got about 10 steps to go through here to show you guys how to solve this, or how it's solved. You know, it doesn't have to take that many steps, but if I skip steps, someone's bound to ask me a question. So the other thing is too, I'm just going to start putting the equal sign. I'm not going to just keep writing RMS out. So just this will be equal to U for the time being until we get towards the end, so I don't have to keep writing out 2 pi ft. So anyway, and I may have to erase some of this, I'm not sure. So the first thing we're going to do, if I work with this problem like it is now, and I can solve it the way it is, but it'll take, to actually do it properly, it'll require what they call a double integration. In other words, I'll have to actually integrate twice to get that to fully come out. So there's another way of doing that. We're going to use what is known as a trigonometric identity, and I'll show you what that is here in a minute. 1 over t, 0 to t, b squared peak times. Now our trigonometric identity is we're going to find something that we can work with a little easier than sine squared. Well, sine squared works out that there's an identity that it equals 1 minus cosine 2 times this mess, and I'm going to call that mess u, divide by 2, and we'll do dt. So I just changed the sine squared into 1 minus cosine of the angle here, and then divide it by 2. And that's called a trigonometric identity. There are literally hundreds of trigonometric identities, so that's just one of them. Now, the other thing is, with calculus, remember this u has got a t in it. So this is a function cosine of that t. That is what the calculus problem is dealing with, is with t. Okay? So anything that's not associated with that t can come outside of the integration. Well, v squared p, or voltage peak squared, has nothing to do with the t. It's not a function of it. It's actually just a number. It'll be a number that you plug in. You'll take your RMS, whatever this comes out to equal to, you'll take that times v peak, whatever it is. In the case of what we were showing earlier with the scope and everything, it was about 170 volts times RMS to get the 120. So this is just a number. It's not any type of function or anything else. So as far as the integration is concerned, it serves no purpose. So I can bring it out. I can bring it outside to here. I'll have v squared here, peak. But also due to algebra, if I got that v squared peak out here, I can actually take it outside of the square root sign by just taking the square root. Well, square root of v squared is v. So I can take it out and I'll end up with v and peak. Only reason the p's there, just to let you know, it is the peak, just one peak voltage. 1 over t, definite integral t. Now I don't have that in there anymore. So that's 1 minus cosine of my 2u. Again, remember u in this case is 2 pi ft. Divide by 2 dt. Okay. Now, using some basic math, I can split this up. If you remember your fractions, when you do addition or subtraction of fractions, use a common denominator. So I can actually split this up where it's 1/2 minus cosine of my 2u over 2. That's the same thing as this. So that's what we're going to do. We're going to split it up. So we take, and hopefully this is, yeah, still on, because I can't get to everything on the camera here, so I'll have to be adjusting it every once in a while. VP 1 over t, definite integral of 1/2 minus the cosine of 2u again remember u is 2 pi ft, divide by 2 dt. Now, something else I can do. This is the same thing as this, times cosine 2u. That is that. Same thing, doesn't matter. All I did was divide it out from the 1/2, leaving me a 1 up here. If I take this times the 1, I get that. I get this. So that's going to be our next little thing, and we're actually going to kind of, well, we'll keep going. I need to adjust you and down a little bit. Okay. Now, that equals VP square root 1 over t, my definite integral of this 1/2 minus 1/2 cosine 2u, parentheses there, dt. Now, we're going to do something that is part of calculus. Whenever I have an addition or subtraction or things like that inside the integration, well, then I can rewrite the integration so it's integral of this minus the integral of this. It's something I can do. That's allowed in the rules of calculus. So that's what we're going to do. At the same time, we're also going to pull the 1/2 completely out. And what I mean by that, we're going to take it out of all this because it can come outside the integration as well. And we're going to pull way out. And, well, I'll show you. 1 over t, and I'm going to take this, we're going to put a big parentheses here, and pull 1/2 here. We're taking it out of the integration, and we're going to split the integration up. Definite integral t, and that'll be dt, because of this here, minus 1/2 0 to t of cosine of my 2u. Again, remember u is 2 pi ft, and dt parentheses. I can get you turned down here just a little more. Okay. Now, we're going to take the 1/2 out, combine it with this. It's going to come out and look like this. 1 over t, okay, times 1/2, because they're going to be out here. Well, you know, simple fractions is if you got two fractions multiplied together, you multiply the numerator first together. That would be 1. 1 times 1 is 1. And you multiply the denominators together. Well, 2 times t is 2t. So that's what we're going to end up with out here. So we have VP square root so we have 1 over 2t. We'll pull them halves out. That'll be times integral definite of dt t minus the definite integral of 0 to t of cosine 2u dt. Okay, we are now at a point that we can actually solve the integrals. And that's what we're going to do. Oh, this will equal VP. Okay. Move this up just a little bit. It's kind of hard to write. Times my square root. We have 1 over 2t right now times this. Now when you pull a definite integral out, the way you write it, we put a bracket. The integration of dt is just t. That's what it equals. Put another bracket. Then we put our definite integral limits right here. That just tells us that we're going to take that t, and we're going to set it at t and subtract from the top one, subtract from the bottom. Now that's minus. Again, we have this one here, we put a bracket. Now, the integral of cosine is sine. So we'll put sine. Now is when we're going to pull the u out and give it some value again. Remember, u is 2 pi ft from above. Well, it's 2 times that. So 2 times 2 pi ft is nothing more than 4 pi ft from 0 to t. That's the solution for the two integrals. Now we take this on, keep working it out. VP square root now we've got to figure out what these are. Had a bracket there. Okay, this works out to be t to itself is t. This is not times t. This is is a variable, but it's going to have a value. Normal definite integrals, you would have like 0 to some number, like say 3, and then you just substitute the 3 in here for the t. You don't take t times t be squared, because then that would make that 9 and it wouldn't be accurate. So anyway, we just substitute that in, t, and then t is 0 minus 0. Subtract this one here is sine of 4 pi f t itself minus sine of 4 pi f 0. And all that's times 1 over 2t. Alright, now first let's look at these guys. 4 pi is just twice 2 pi. 2 pi is a complete circle. 2 pi equals 360 degrees. Alright, 2 pi radians is the same thing as 360 degrees, or a complete circle. all the way around. Sine of whether it's 2 pi or any multiples of 2 pi, such as 4 pi, is the same thing as sine of 360, and sine of 360 degrees is 0. So, and it matters not what f and t is doing here, because anything multiplied that is just a multiple of the initial 2 pi. So it's always going to be that completed circle. So this will be, and we'll just put down here, 0. This has already got a 0 in it, so everything times 0, 4 pi f 0, 4 pi times f times 0 is 0, sine of 0 is 0. That's just the other point of the circle. You go around full 360, you start at 0, go around full 360, you're back to 0. So that's just minus 0. Okay? So these two end up being 0. This is just all 0. Now over here, we have 0 and t. So that's all we end up with, just t minus 0. Okay, that's that. So when I take and reduce all this down, get rid of all the zeros, because zeros matter not. They're just 0. What I end up with equals VP square root of 1 over 2t, make sure that's in there, okay, times t. That's it. Everything else is 0. Okay, now what does that do for me? Well, I'm not done yet. If I take this times, it'll be t over 2t. Well, the t's cancel, because t over t, I don't care what value it is, t over t is 1. If I let t be 3, it's 3 over 3. 3 divided by 3 is 1. I can let t be a million. A million times a million, or a million divided by a million, is 1. So it doesn't matter. So these cancel out. And let me rotate you down. I want you to be able to see this. Cancel out and come out to equaling this. VP, voltage peak, equals the square root of nothing but 1/2. Okay, okay, that's great. Well, according to dealing with erratics, this is the same thing as the square root of 1 over the square root of 2. That's the same as this. Well, what does that equal? VP square root of 1 is 1. Take any calculator, take the square root of 1, it's 1. Over the square root of 2. And that, right there, is RMS for a sine wave only. But it's RMS for a sine wave, like what we was showing. If you had some complex wave, then things start changing way back at the beginning, and you actually have to work the integration out, and it'll come out to some different value than this. But that is, now what is 1 over square root of 2? Well, 1 over the square root of 2 equals, rounded roughly, 0.707. So I take that peak voltage, in this case 170 volts that we had at the beginning of the video, times 0.707, it comes out pretty darn close to 120 volts. Just a little bit over that, but real close. Because I'm rounding numbers here and everything. That is your RMS for sine wave. 0.707. Now that's what you always use. So we started way back here with this original formula, and with the sine wave we broke it down, solved it, and came out to this. Okay, Now, we need to talk a little bit about some other stuff. Before we actually get into AC in depth, we need to talk about trig. So, that's what we're going to do. And let's see, let me widen you back out here a little bit. Focus. Alright. Might bring you down just, well, no, that's good. So, get to my notes here. I keep notes because otherwise I forget to get stuff in the video. Alright. There is a circle called the unity circle, and it is a really great little thing to work with when it comes to trig. And we need the trig to understand AC. There'll be some problems that you just at least know that the trig's there and kind of have a feel for it, so it's not a surprise to you if nothing else. Why a circle? Well, look at this. Sine wave. What if I took and flipped this so that I got a circle. And a circle right there. Not a perfect drawing, but it's a circle nonetheless. Okay? That's why a circle. Because that's really what it is. That's all a sine wave is. It's going from a particular angles, rotating through, around, back around, until it finally comes back to a point where it started from. So we're going to use a circle called a unity circle, and I'll show you why it's called a unity circle. First, we take a rectangular graph. This is Y, this is X. And let me kind of get you up here. Maybe zoom it in just a hair. And do just a slight little rotation. Alright. Now, hopefully, I can get a halfway decent circle. Yeah, way off. Anyway, unity circle is such. It's a circle whose radius is 1. And what that means is simply, as I rotate that radius through, then where it crosses the x-axis is plus or minus 1. Where it crosses the y-axis is plus or minus 1. But it's 1. Now, why is that so important? Well, if I drop, for trig, if I drop, oh, let's use some different colors here. Right. If I drop straight down from here, there's a right triangle. Or, if I come across this way, there's a right triangle. Either way, I form a triangle from that circle. No matter where that's at, it always will form some sort of triangle. Now, let's go ahead and pull this out of here for right now. We'll come back to it. Maybe I can draw it better. Let's look at the triangle. We'll just kind of draw an arbitrary right triangle here. We got an angle here. We'll call U. This here is the hypotenuse. Name H. This side here is the adjacent side to U, my angle. So we call it A. This side over here is the opposite to the angle, so we call it O. Now, trigonometric functions are ratios. They're ratios of these sides for that angle. If I take sine, cosine, or one other one known as tangent of that angle, I'm going to get a ratio of two of these sides. So, we'll come over here. Sine of u equals the opposite side divided by my h, my hypotenuse. And you can use non-capital letters if you want. It's perfectly fine. Some people teach it with capitals, some people teach it with small letters. The only reason why I deal with capital letters for the most part is because there are some other areas that have a small a and a small h that would be also dealing in this. So cosine u is adjacent sine over hypotenuse, and then tangent of u is opposite over adjacent. Now, for everybody who wants to try to remember these relationships, as long as you remember hypotenuse, opposite, how it poses to the angle, and adjacent, remember those terms, then you can remember this by a saying. Oscar has a heap of apples. Okay? That's all you gotta do. Oscar has a heap of apples. There's probably others. There's probably some that are X-rated, I'm sure. Now, remember our unity circle. See if I can, well, before I draw those in, let's just draw a circle. Try to draw kind of roughly. Alright. Okay. This right here, the 1, that radius, is this. It's hypotenuse of the triangles, whichever one I want to use. Okay? Well, if I use the unity circle, use 1, then h becomes 1. So in a case like that, then I can rewrite sine and cosine as this. Sine u just equals opposite. Cosine u equals adjacent. Because h is 1. So opposite divided by 1 is just opposite. Adjacent divided by 1 is just adjacent. But these also equal something else. We have the x-axis and the y-axis. Excuse me. So, sine is the opposite side of the angle. Sine is y. You know, if I rotate this around and drew it a little differently and everything, here's my angle, but this is the same thing as this right here. It's the same length. These both being 90-degree angles, that's completely horizontal, that's completely vertical. So this length has to be this, which is y. So sine, which is the opposite side, which is y. Cosine, which is adjacent, and that's this side, is x. Now that'll become important later. Now I was going to talk a little bit about just a teeny bit about identities. Well, let's look at the right triangle. Anybody's had high school math and geometry heard of the Pythagorean theorem, Pythagoras, the solving of a right triangle, a squared plus b squared equals c squared, or one side squared plus the other side squared gives you hypotenuse squared. So basically, if we take opposite side plus adjacent side equals the hypotenuse side. So this one squared plus this one squared equals this one squared. But since I'm using the unity circle, that is 1. 1 squared is 1. So opposite squared plus adjacent squared equals 1. Okay, what does that mean? Well, what's O? O is sine. Oh, okay. So sine squared plus what's adjacent? That's cosine. Cosine squared equals 1. That's one of the primary trigonometric identities. Sine squared plus cosine squared equals 1. And it comes back to this here. The 1 is the hypotenuse. And see, sine is y, or O, squared. It's this side squared. Cosine is this side squared. So it's just the Pythagorean theorem. Pythagoras theorem. So, with a little algebra and actually one other trigonometric identity, I can rearrange this and rewrite this so that sine squared u equals 1 minus cosine 2u divided by 2. That's another trigonometric identity. Comes from this one here. Is where it comes from. Just rewritten with a little bit of algebra and one other trigonometric identity will give you that. Now, what does all this got to do with AC? Well, where and what this does, it has to do with something that I'll be showing you as time goes along that looks something like this. Come down like this, and well, actually I'll probably just go this way. And I'm going to have like a little arrow here, and a little arrow here, and a little arrow here. And this is going to be an L, and well, actually it's going to be X sub L. And this is going to be C, or X sub C. So I better just put those in there. And this is R. And what this is dealing with impedance, which we will be dealing with. We're going to be talking a lot about impedance, and X sub L, which is inductive reactance, X sub C, which is capacitive reactance, and of course R is resistance. We're going to be talking about all these considerably. Now, where you can think of this as going positive and this going negative, basically. But why are these two opposite each other? Well, this has to do with current and voltage and how they react to each other in either a pure inductive or pure capacitive circuit. Way back when I talked about something, and I talked about Eli the Iceman. And what it was simply this. You have Eli, well, anyway, when you deal with an inductor, Eli, voltage leads the current, or the current lags behind voltage in an inductive circuit, Eli. by 90 degrees. In a perfect inductive circuit with a perfect inductor, it'll be exactly 90 degrees. And realize these are 90 degrees here. So the voltage leads the current by 90 degrees. That's what this is. Iceman. In a pure capacitive circuit, now the voltage is lagging, or the current leads the voltage. And that's what this is. Now, we've got right triangles. We're dealing with making up an actual impedance, which is actually the hypotenuse. And so impedance will equal the square root of inductive reactance minus capacitive reactance, X sub C, plus resistance squared. Now we have resistance always in there. And the reason why is because no circuit's perfect. If nothing else, the inductor, and you all know this, you measured coils in radios and stuff, they do have a certain amount of DC resistance. This is about where I'm going to leave off. We'll pick up with this and talk about it more on the next video. But I'm going to leave off with this, and one other little point. I have made it over 1,000 subscribers, so I want to thank you guys for your support, and all my new subscribers and stuff. So thanks again, and thanks for watching. I'll see you guys on the next video. If you like my videos, please subscribe. If you like this video, give it a big thumbs up. And probably the next video will either be on the radio or the TV circuits. See you on the next video.